Okay, so, big test tomorrow. That'll be the last of the really like big tests.
Oh. When we're talking big, are we talking like importance or like length?
All the above.
Okay.
Well, just like, it'll be like all the other tests.
You said four bigs.
It's like this.
No. We have another unit.
You said
It's
four of
just
them.
easier.
You said it's.
The last big test. You're still gonna have one more test, but that's just like, you know, hybridized orbitals and gas laws and molecular
A
physics.
bunch of other words I don't know.
That was tomorrow.
I
That's tomorrow.
can take that test after school there.
Okay.
Yeah, that's- Okay, so let's just kind of go through this start to finish. So on the yellow sheet, okay? So on the yellow sheet, here's the whole point of this, is that you're given a chart of bond enthalpies, okay?
Why is that positive?
Oh, I got it.
With the correct sign?
No.
Does it not let you write with your finger? Oh, that probably would be legible. I'm sorry. What could I say?
Negative 1369.
Yeah.
Or Kim, you should just go steal one of the pins from the art classes.
I should just get a whole new iPad.
Because it was for the reaction.
Why don't you have the fancy laptops that flip, like the other teachers?
I've got one, but mine was just junk and it didn't work.
Like Miss Houseman's, that was always broken and she always
matches.
Just
yelled
tell
at it.
boot camp that you need a fancy new iPad.
I told Dr. Botts and I had that discussion just this morning. And he says he'll get me one. We'll see.
Threaten to quit, Berg. Tell them they have 1 week.
Literally what holds like
No,
the top
we're- I have
1%
13 and a
of
half
every
days left. We have to
class.
stay 13 and a half
Together.
days.
Wait, what's that?
We're in the middle of the day right now.
What's the AP?
We need you to finish out high school. What's one? Oh, the cup power?
Yeah.
I don't know why it's there, but I just have some nerves like throw something. So I'm part of it.
It's sitting next to me and I have a ruler and I
Yeah,
really
I-
just want to,
I would have had to move if I'm not gonna.
I'm so tempted. Which one is negative?
Hey, now it like, if you turn it sideways, like it doesn't. Oh, now it does.
We're just gonna have to.
That doesn't make sense.
No, it didn't. You were physics on yours.
Yeah.
Mine was just like that reaction shouldn't happen or something.
Oh my gosh, it's the same thing. Yeah, you only made one chart.
Yeah, I mean, this class we break physics, and physics breaks us.
I mean, I guess you could have been.
I still don't understand. I figured.
What, physics?
The physics one. Yeah, I still don't understand that one.
You guys find anything wrong with my work?
The one that's due today.
Nope, it looks great, Kevin.
Okay.
Guys,
I just didn't have my
This is
books.
As long as everything tracks.
I mean, it looks right.
Mine are
I
55.
feel like this one is supposed to be negative because it's forming a bond.
Mine
So you're being
after they-
this
If
has
we
to
need
be
1.4,
but I don't, I'm not sure on these ones, like I don't, the formation, because when you form bonds, energy is released. So energy leaves the system, so it's neg.
Okay, did you get part of E?
I got everything else. Yes, I got
E and negative.
gonna go?
Like that.
So what do you do when it doesn't recognize the Apple Pencil?
I cry usually.
because we need to find the
I
delta.
cry, hit my iPad a few
I
times.
just don't review because it's me.
Usually it works.
Yeah.
I go-
So I don't.
With my Apple
So
Pencil,
I just calculate this and then
hit it a little
You can
bit.
do this, Bert.
Yeah.
that's all I need. But then these should, 57 should do that. This is the same experiment.
Miracle of miracles now it works. Okay,
It just changes.
are we filming?
Yes, we are.
Okay, hi 1G, hi Graham. You've watched me into a fit of rage with technology. Anyway, so back to our story. So you've got the nitrogen. Now, notice there's a couple of things about this that are important. Notice that the nitrogen bond is extremely high, okay? Which is cool, actually, because the vast majority of our atmosphere is nitrogen gas. So notice that that has a very, very, very high bond enthalpy, and once we get into this, you'll see why. That there's actually a triple bond that exists between nitrogens. So nitrogen isn't a noble gas, but it pretty much acts like a noble gas, mainly because it has such a high bond strength that it's incredibly difficult to break that bond. Now, oxygen, that works really, really well. Oxygen, this is why we talk about redox reactions, because of oxidation, because oxygen reacts with things. So, it is okay that nitrogen doesn't. So basically, we have a lot of nitrogen, but we don't have to worry about it reacting with anything. If nitrogen reacted the way oxygen did, like when you started a fire, oh, bad things would happen, okay? Like literally, if you started a fire, like you could not shut it down if nitrogen reacted the way that oxygen did. So like if the roles are reversed, and we had like 77% oxygen and 22% nitrogen, we wouldn't be here, mainly because of the fact that you have such a high oxygen content, like everything would just go up in flames. Okay, so your answer to number one, because you got to break the bonds that hold the nitrogen, and you got to break the bonds that hold together the fluorine. So that answer on number one should be around 1400. Okay, so that's how much energy you have to dump in to break all of the bonds. Then it's just a number. It's just a number. Okay, don't make it positive, don't make it negative. That's just how much energy that you have to put into it. Okay? Then the energy involved in the formation of all of the bonds. Now, you're making nitrogen trifluoride. Okay? So each one of those bonds, each nitrogen fluorine bond is going to involve 272 joules. So each one of these is 272 per mole. So you got to take 3 times 272. Then there's 2 moles of that, so you got to multiply 2 by all of that. So your answer to number 2 in round numbers is about 1600. Okay? So you got to dump in about 1400 joules of energy to break all the bonds, but then you're going to release about 1600 kilojoules of energy in the formation of the bonds. So since you're releasing more energy than you're putting in, this is going to be an endothermic or exothermic reaction. It's exothermic, okay? So now, when you get to number 3, what's the total enthalpy change? This is where this should be a negative value, because of the fact that's going to be a negative value, because, oh, this is an exothermic reaction, we're releasing more energy than you put into it. So, now let's look at this in terms of delta G equaling delta H minus T delta S. Okay, so this is what, at this point, you should be able to think through. What's the sign of your delta H going to be, based upon the information that you have?
Negative.
Negative. I'm going to have a negative delta H, okay? And even if you didn't have the numbers, you could probably look at that and go, yeah, I got to break some bonds, and I'm also forming a bunch of bonds, okay? Now, I got a negative delta H. Based upon the fact that you have 4 moles of gaseous reacting, and you have 2 moles of gaseous product, okay? So you're going from 4 moles of gaseous reactant to 2 moles of gaseous product. Based upon that, what should be the sign of delta S? Just based upon moles of gas. You're going from 4 to 2. Negative, okay? So you got, based upon that, you've got a negative delta S, okay? So, based upon that information, is the reaction temperature dependent?
Yes.
Yes, it's not always going to happen, okay? It's temperature dependent. Is it temperature based on low values or high values? Low values, because of the fact that you've got a negative delta H minus a delta S. I'm telling you, there are 4 things, there's any number of things you have to know going into tomorrow. One is the 4 combinations of delta H and delta S. Positive, positive, negative, 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 positive, positive, negative, okay? You have to know those cold, no pun intended. Negative delta H versus a positive delta H, endothermic, exothermic. Work being done on a system versus being work done by a system. Heat flowing into a system, heat flowing out of a system, okay? Those are things you just got to know. All right. On the other sheet of problems. So, let me see some of these assignments. So let's start with the circled ones that start with 41. So if you look at those questions, I got my own. So let's look at some hidden things that happen in 41. So even if you just read 41, it says it's quite common for a solid to change from one structure to another in temperature below its melting point. Okay, so if you read 41, so right away you can glean some information. You're talking about a melting point. So what does that tell you about being temperature dependent? Is it temperature dependent or not temperature dependent? It's temperature dependent, okay? So anytime you have something that's, you have to have a certain temperature for it to exist at, or a tipping point at a certain temperature, you know it's either both positive or both negative. That's your only options, okay? If it wasn't, then there would be no need to mention the temperature because it would always be spontaneous or it would never be spontaneous, okay? So right away you've got that. So, for example, sulfur undergoes a phase change from rhombic to monoclinic at temperatures above 95 degrees Celsius. Okay, so you're told that this is going to happen at temperatures greater than 95 degrees Celsius. Cool. It's above a certain temperature. So what do you know about delta H? Morgan? What about your delta S? So right away, even within that, without them giving you any information, you're going to have a positive delta H and you're going to have a positive delta S. Okay? So that reinforces this idea, oh, this thing is temperature dependent. So since it asks, predict the sign of delta H for the process S rhombic turning S monoclinic. Okay? So again, it's either positive or negative. Then based upon that, which form of sulfur has a more ordered? Now, the whole key to this is that I asked for the one that's more ordered. So, if it's more ordered, and this is what you have to think through, if it's more ordered, is there more entropy or less entropy? Less entropy, okay? So more ordered means less entropy. Less ordered means more entropy. So my room is kind of lacking order, okay? But I do that just for this lecture. So with less order, there is more entropy. If I walked in and the room was like completely clean and everything, you all would be like, who are you and what have you done with Burkina? You know? Okay. All right. Now, so we have a stack of cups up here, okay? 1G and Ram, you guys can't see this. So right now, that's very ordered. So if we knock this down, and don't, okay? But if we knocked it down, is that going to automatically, at some point, going to reform the pyramid?
No.
No, why not?
Gravity.
Well,
Photons.
Mother Nature's gravity photons.
You taught us well, Berg. We know what the answer to everything is.
Gravity or photons?
Sun.
Or the sun, you left out the sun.
Oh, yeah, sorry.
So, because Mother Nature goes, hey, I like it high, so right now, does that stack of cups, or stack of caps, is that ordered or not ordered? Very ordered. So does that have much entropy right now?
No.
No. Now we knock it down, that's going to go to a higher state of,
Entropy.
and Mother Nature likes that.
Hotness.
Okay. Now let's talk about 43. Okay? So there's some information that you have and you don't have on 43. So let's just start with this on 43. So you have 2O as a gas turning into O2. So let's just look at this in terms of bonds, okay? On the reactant side, do you have to break any bonds? No, because these are just two oxygen atoms. So you have two oxygen, so you don't have to put any energy in to break the bonds, because they're two separate oxygen atoms. You're going to make oxygen gas. Going to come together. So the only thing you're going to do is form bonds. So since the only thing you're doing is forming bonds, what's going to be the sign of delta H?
Negative.
Negative. So now you got a negative delta H. Okay? Well, now I know that. And I know that solely because of the fact that all I'm doing is forming bonds. Now, what's going to be the sign of my delta S?
Negative.
Why?
Less moles of gas.
Yeah, I'm going from 2 moles of gas to 1 mole gas. So instead of these individual oxygen atoms being able to fly around willy-nilly, it's like, no, you got to go together. So imagine this is kind of like, if you go with this analogy, in elementary school, sometimes teachers make you have like a buddy that you walk down the hall with. Do they still do that? Okay, right? Yeah, your study buddy. From an entropy standpoint, why are they doing that?
Because if
mess
we're linked
around.
together, we're not gonna just run around.
There's not as much potential for entropy, right? So elementary teachers do that to decrease entropy. It's like, oh yeah, I'm going to view that completely differently now. But that's why they're doing it. If you're an elementary teacher, and this is why I couldn't handle teaching elementary kids, there's just way too much random entropy, too many photons, okay? Too much disorder. It's like, nah, I got a puppy. Don't care, shut up. So, no, seriously, that's how I would be, okay? Like when I go over to the grade schools and I read my children's book to them, they're like, I got a puppy, I have a dog.
And you're supposed to say, oh my gosh, that's great.
What's your dog's
I
name?
do. But
You
that's
could
fine.
pretend for an hour.
But this guy says like, good, great. Okay, any other questions? Okay, thank you. All right. Now, let's talk about 44. So, hydrogen cyanide is produced adjusted by the following exothermic reaction. Okay? It's exothermic. What's the sign of delta H? Negative. So you have negative delta H. So, I know on 44, I get a negative delta H. What's going to be the sign of delta S when you look at 44? How many total moles of gaseous reactant do you have? You've got 7. Okay, moles of gaseous reactant.
Positive.
Oh, and then you have 8 moles of gaseous reactant. Product, I'm sorry. Of reactant. So you're going from 7 to 8. What's going to be the sign of delta S?
Positive.
So you have a negative delta H and a,
Positive.
is it always going to be spontaneous?
Yeah.
Yes.
So on that question, it says, why do you need it for thermodynamic or kinetic reasons? Thermodynamic, that would imply that you have like a positive delta H and a positive delta S, and you have to run it above a certain temperature, okay? You don't. You got a negative delta H, and so even you could even stop right there. As soon as you have a negative delta H, you know you don't have to run it at high temperatures, because if you have a negative delta H, even if you have a negative delta S, you would run it at low temperatures. So I don't need, the thermodynamic reason would be, hey, I got to run it above a certain temperature. Ugh.
I guess it is.
No. I do. I'll do that.
He's annoyed by it.
All right. Or Morgan.
No, I looked away on purpose.
Oh my god.
Sorry.
We're going to go over that in class.
Finally.
And there's the other part of the answer key, or the review with the answer key on it. Okay. All right. Let me see. On 47, this is one where you have to go through and you have to look up the thermodynamic data. So basically what you're saying on 47 is that we're going to try and make acetic acid. We've worked with acetic acid a lot. Obviously, acetic acid is basically vinegar. So obviously we somehow have figured out how to make acetic acid. Okay, we use it a lot. So there's two ways that you can do it. One basically is you take a methane molecule and a carbon dioxide molecule and you combine them to make acetic acid. Your other option is that you take methyl alcohol, CH3OH, react that with carbon monoxide, and then you produce acetic acid. So there's two ways you can do it. In both situations, you produce acetic acid. So which would you choose as commercial method for producing it? Now, so here's the only way you can do this is to go through and calculate your delta H, your delta S, and your delta G. Now, depending upon how you wanted to do this, if you wanted to just get your delta H and then use the T delta S and use like standard temperature of 25 degrees, okay, you could do it that and then calculate the delta G that way, or you could just go through and calculate your delta G straight up. But here's the problem. If you just look at this, okay, you really can't, you kind of have to get that delta H and delta S to try and figure out, okay, what's actually going to happen. So what you should see on that first method, your delta H is a negative value, your delta S is a negative value, and your delta G is a positive value, okay? On the second method, you still have a negative delta H, you still have a negative delta S, but now you have a negative delta G. So even if you wanted to, could you produce acetic acid from that first reaction? No, okay? You could try, it's not going to happen. You're not going to win because of the fact that it's not spontaneous, okay? Because if you look at that, you got a negative delta H and a negative delta S, but at that point, because you have the two negative values, at room temperature, you're below that value and you're getting a delta G that's positive. Now, could you make it spontaneous? Yeah, you could, because you got a negative delta H and a negative delta S. But you would have to get it below a certain point to make that happen. So basically that question then is, what temperature conditions would you choose? Assume delta H and delta S do not depend on temperatures, which is a bit of an assumption. So obviously you would choose reaction number 2, because that's the only one that's spontaneous at room temperatures. Okay, cool with that side. All right, now on the back side. So let me give you some hints on some of your answers. On 49 through 56, 4 of your answers should be negative. Only one of them should be positive. Okay? So on 49 through 56, 4 of them are negative, 1 of them are positive. When you get to question 57, okay? So let's talk about 57. So on 57, and Charles, this is kind of an important thing, okay? So,
We love you, Charles.
okay, you gotta use delta G equals delta G naught plus RT times the natural log of Q. And the first thing you have to do is figure out your delta G naught value. So on 57, when you go through and you look at the thermodynamic data, because if your delta G naught is wrong, everything is going to be wrong, okay? So your delta G naught in kilojoules per mole should be around -5, okay? So that's that -5-ish. Now, here's the kicker, and this is what you have to be careful of. That's in kilojoules per mole. What units is your R value in? Joules per mole Kelvin. Something has to give, okay? You either take the delta G naught and change that into joules, or you take the R value and change that into kilojoules. I care not. Now, you have the natural log of Q. So let's talk mathematics, okay? So, if you were to try and find a point of equilibrium, what would delta G equal? Not delta G naught. At equilibrium, delta G would equal 0. And this is where you can go through and you can try and find that value of K. So let's look at the mathematical side of this. If you want delta G to be a negative value, okay? So first off, you got a negative delta G naught, which says, hey, at least it has the potential to be spontaneous under standard conditions. So, and here's the hidden math on 57. So on 57, you have 2 NO2 and then 2 dinitrogen pentaoxides. So in this, no, it's just, there is no 2. So if the reaction goes forward, what's the sign of delta S? In forward reaction.
Positive, no, negative,
Why?
less moles gas.
Because you're going from 2 moles of gas down to 1 mole of gas, right? Based upon that, you have a negative delta S, okay? You have a negative delta G. Cool. So on that negative delta, so this is what, again, what you need to be able to think through and go, okay, cool. I got a negative delta G, but I know I have a negative delta S. So if this reaction is going to happen, what sign do you know your delta H has to be?
Negative.
Negative. Because if you have a positive delta H with a negative delta S, this reaction is never going to happen. So right away you go, oh, this has to be an exothermic reaction, okay? Because that's the only way it can work. Because you know you have a negative delta S, which is, the delta S is the low-hanging fruit. You can look at a reaction and compare moles of gas on the reactant side to moles of gas on the product side. It isn't always true, but vast majority of the time it's true. That's your low-hanging fruit. Oh, great, I got a negative delta S. The reaction is spontaneous, therefore I have to know I have a negative delta H, which means the reaction has to be exothermic, okay? So, if this had been under standard conditions, what would the pressures of everything be?
1.
1. Oh, so then you're taking the natural log of 1. The natural log of 1 is what, Charles?
I don't know.
Math nerds. What's the natural log of 1?
0.
0. So if this is under standard conditions, everything's at 1 pressure, what's that entire value then going to be? 0. Guess what? Delta G would equal delta G naught, because you're under standard conditions of 1 atmosphere of pressure, okay? So, here's what you've got on 57. And do not forget, because you have that 2 out there, and it's products over reactants, so it's the pressure of your N2O4 over the pressure of your NO2. But, Kevin, what do you have to do with the NO2?
Have to square it.
You have to square it, okay? So, what you should see on 57, and this was that you got to calculate delta G in all 3 cases. So, on 57, you should see basically all 3 options. You should see a situation where the reaction shifts to the left, one that it shifts to the right, and one where it's at equilibrium. Okay? So you should 1 shift left, 1 shift right. On 58, both of those on the delta G values should be, unfortunately, and be careful about this, about 10 numeric values above my age. Be careful how you answer that.
And negative.
And negative, yeah. And negative. So, if you look on 58, there's some read the instructions on 58, because you want to calculate delta H naught, delta S naught, and K. So those are the first 3 things that you need. Do not randomly write down numbers and think Burkamp will know what the numbers are. No, Burkamp won't know what the numbers are. Okay? So you tell me, here's the delta H, here's the delta S, here's your K value. Your K value should be a really big number. Like something times 10 to the 5th big. Okay? Like a really big number. So what does that tell you when you have a big K value?
It's gonna happen.
It's gonna happen. Okay? It's gonna happen. So, now unfortunately it does happen, but you still have to have it under a tremendous amount of pressure to make it happen. So, and this is, like, I want to get this out of your minds. So, we have a spontaneous reaction. But you have, let me give you an example where you have a spontaneous reaction, but it's not going to happen, if that makes sense. So, in the back room, I have a container of pure hydrogen gas, okay? I have a container of pure hydrogen gas. Our atmosphere has a lot of nitrogen in it. If I say, hey, Miss Houseman needs some fertilizer for her plants, I'm just going to go open up the hydrogen tank. That'll combine with nitrogen in the air. It will rain ammonia, and we'll fertilize the plants.
That would not be good.
Well, no, it would not be good.
Well, you have to.
Okay, number 1, if it happened, what would happen to the pressure in the room?
Decrease.
Because it would rain ammonia, right? So you're taking the nitrogen in the room, there's a lot of it, and you're combining it with hydrogen. It's like, oh, whew, can't breathe. Okay.
Blood would boil, so you'd be really clean.
All right. Any other questions? If you want to hold on to this assignment and hand it in tomorrow, you can. Okay? It's up to you. But when you hand it in, I want the yellow sheet on top. Yellow sheet on top, then the sheet, and then the answers to that. Okay? All right. Are we good? Kevin, stop yelling. Kevin. Give me 1 second.